There are several formulas for the area of a triangle. 1/2 base times height. There's Heron's formula. There is the semi-perimeter times the radius of the incircle, or the in radius. And then the one that we're going to use today is the product of the three sides divided by 4 times the circumradius. If you're unfamiliar with this formula, I'm going to prove it to you now. Here is our circle, and we're going to draw triangle ABC inside of our circle. We'll call this circle with center O. I'm going to draw a height from B to the opposite side. We'll call this E. This is the height of our triangle. And I'm going to draw a circle to form a diameter, and we'll call this point D. And again, this is the circumradius. I'm first going to start this proof by proving that triangle BAD is similar to triangle BEC. To do that, the first thing I'm going to do is I'm going to connect points D and A. So here is triangle BAD, and then we have triangle BEC. Angle BAD is 90 degrees. And you can see that because BD is the diameter, and this angle cuts off 180 degrees, and so the angle is half of that, so it's 90 degrees. And we've defined angle BEC to be the height of our triangle, so it's also 90 degrees, so these two angles are equal. The other angle is angle BDA. It's an inscribed angle, and it cuts off arc AB. We have another angle here, angle ACB, that also cuts off the same arc, AB. So these two angles are the same. We have two angles of two different triangles that are congruent, so by angle, we have that these two triangles are similar. Let's take a look then at the corresponding sides of these triangles. BD is the hypotenuse of triangle BAD, and let's compare it to this other side, BA. The hypotenuse of triangle BEC is BC, and the corresponding side is BE. Okay, let's outline our substitution. So BD is the diameter of the circle. BA has length C. BC is lowercase a, and BE is the height of our triangle. So let's do these substitutions. Let's use our easy formula for the area of a triangle, and we're going to solve for the height. And we'll substitute that here and solve for the area of a triangle. And there you have it. So let's return to the problem. The next thing I want to show is that for a given circumradius, if we want to maximize the perimeter of a given triangle, so let's consider this circle with a given circumradius, and let's draw a couple of triangles with the same circumradius, this red one and this green one. Notice that as we get closer to a triangle that looks more like an equilateral triangle, we will maximize not only the area, but we also maximize the perimeter. So it seems like maximizing the area of a triangle with a given circumradius is also going to maximize the perimeter. So my strategy here is to maximize the area, or maximize this expression. We can see that we can maximize this quantity by achieving a circle that is close to being an equilateral circle. So something like A is equal to B is equal to C. And the area of an equilateral triangle, let's say with side length A, is A squared root 3 over 4. If we have ABC is equal to the area of a triangle times 4 times the circumradius. Also, let's try to get, we want to fit this triangle inside of a circle with radius 20. So let's start off with a circumradius of 20 and see if we can get a triangle that's slightly smaller than this. So doing our substitution for the area of an equilateral triangle and solving for A, it seems like our maximum perimeter of this triangle is going to be something like 3A. This is the target round, so we're allowed to use calculators. You'll see this is approximately 103.9. We want our perimeter to be an integer, so we want this to fit inside the triangle, so we're looking for something slightly smaller than this. So the maximum perimeter is 103.